Good afternoon, friends. I myself, Dr. Kushal Bhattacharya, and we are going for our second lecture in cone clutch. So previously we have been discussed that there are two theories which are involved to solve this to solve this integral equation. That is the axial pressure from the elemental area to the full section of the cone clutch. That is the when the inner cone is coming when this inner cone is coming in contact with the outer cone, we have deduced an expression for a very small amount of strip. So based on this we have found this axial force, that is P 2 pi in the limit of d by 2 and small d by 2. This is the small d by 2 and this is the capital D by 2. This is the small d by 2. You see, this is the small d and this is the capital D, and PR dr. This is the expression which we have deduced, which we have deduced in our previous lecture, part 1 lecture of cone clutch. Now I told you that there are two ways, specific ways of deducing these two expressions. One is that you by deducing it the uniform pressure theory, and another is by uniform wear theory. Now a very important consideration comes when we should be considering uniform pressure theory and when we should be considering uniform wear theory. First of all, the very basic thing is that when a clutch is new, that means suppose when an automobile vehicle, you have replaced a clutch or an automobile vehicle with a new clutch, so then the theory applicable is constant pressure theory, because it is assumed that the pressure is distributed thoroughly uniformly. So at that criteria we basically consider uniform pressure theory, where P is considered to be constant. So here you could see we have considered P to be constant. We have considered P to be constant throughout. That is, when the clutch is moving in the axial direction, when the clutch is moving in the axial direction, the inner cone of the clutch is moving axial direction to the outer cone of the clutch. So that in that condition, on the friction lining, the pressure distribution is considered uniform. This happens when the clutch is new, when a new clutch is brought, or when a new clutch plate is brought. So that is the assumption when it is held when you consider a new clutch. Now one thing is that for this we have find out this expression. Previously, if you see my first lecture, you have got this expression P is equals to 2 pi d by 2 in the limit of d by 2 PR dr. So this is the expression. Now we are going to basically, for constant pressure, if you consider constant pressure, then this P will come out from the integration, and we should integrate only on the basis of this radius, which varies from this d by 2 to d by 2. This diameter, small diameter to bigger diameter, and we have integrated it, and we have find out this expression, that is 2 pi. We have find out this expression, that is 2 pi p r square by 2 small d by 2 by capital D by 2. Now what happens basically when we consider this expression, we have got this form. After integration, that is after integration and putting the values, we have got this form. Now see, this is the ultimate pressure, this is not the pressure, this is the applied load. This is the applied load, this is this applied load for a uniform pressure when the clutch is new and we are considering uniform pressure theory. So this is the applied force, this is the applied force given by the have to be given from this side, that is either is given by the driver or by any means to the driving, so that the inner cone of the clutch comes in contact to the outer cone of the clutch. So this is the expression for P. This is pi small p, that is the uniform pressure, and capital D by small d. So this is the actual pressure required when we are considering a new clutch. and we are considering when we are considering new clutch, we are going with the theory of uniform pressure theory. Now if you remember, we have also find an expression for moment. So this is the momentary torque, which is when the clutch is engaged, the torque transmitted. So this is the torque transmitted expression we have previously find out in our previous lecture. Now we are going for this. Now we are basically going for this and see the torque expression. Basically the torque expression comes like this: twice by p r square dr. Now over here you see, as we have taken that the p, that the uniform pressure, so this p comes out. So this p comes out from the expression. This p comes out, and we are integrating only small d by capital D. So while doing this, we have got this expression: 2 pi mu small p, 2 pi v small p by sine alpha r cube by r cube d square by d square. So this is the expression of the torque. This is the expression of the torque. So you have to remember two conditions. This is the applied force required to engage the clutch, and this is the frictional torque which is required to keep the clutch in, which the clutch basically transmitting to the driven shaft. Which the clutch basically transmitting to the driving shaft. So this is the value of the torque. So these two equations you have to remember. This is only possible for uniform pressure theory. Now with this consideration in mind, we are going to a uniform wear theory. So first, uniform pressure theory we have seen what are the constants. Now we are going for the uniform wear theory. Now basically you see, when you go to uniform wear theory, so that means it indicates that the pressure is not distributed uniformly. This happens because every time when the clutch is engaged and disengaged, the friction lining may become worn out, and the pressure will not remain same. The pressure will not remain same throughout. So that is the reason uniform pressure cannot be held for a worn out clutch. So for that reason we have to go for uniform wear. So we are thinking that the wear should be uniform. The wear should be uniform. Now what is the physical significance of wear to be uniform? So how we should model that the wear should be uniform? How can it be modeled? So for this reason we have a consideration that we have considered that for the wear to be uniform, PR remaining constant. This property P into R, that is P multiplied by small pressure. As you can see over here also, the pressure distribution is not same. The pressure distribution is varying nature. The pressure distribution is totally varying nature. So that is the reason behind it. Though that is the reason behind it, as the pressure distribution is in varying nature. So you could see we are considering PR is a constant. This is the physical analogy or the physics behind considering the uniform pressure theory. The physics behind considering the uniform wear theory. So when you consider uniform wear theory, this PR remains constant. Now you could see this. Now you could see this when PR by R is constant. So P is inversely proportional to R. This indicates that as the radius reduces, the pressure increases. So as the radius reduces, the pressure increases. So you could see that the inner lining, the inner cone, that is this one, the inner radius, that is the small d, the inner radius, that is a small d, or that is a small d by 2. Basically the inner radius of small d by 2, the pressure is very high. The pressure have to be very high. So that pressure is taken as the maximum pressure, or it is the permissible pressure. So now we should deal our calculation mathematical model with the basis of this maximum pressure. So this is the maximum pressure, this is the maximum pressure. So we should deal our all other calculation on the basis of the maximum pressure. So that is the basic concept of the design. We should always deal with the maximum pressure. So this maximum pressure we should take into our consideration. Now you see, this expression which we have seen over here also, 2 pi r dr. So this is the expression we should be now operating with. First we have to operate it for uniform pressure theory. Now we should be operating for the uniform wear theory. So now uniform wear theory, you could see 2 pi r PR TR. Now you could see this constant PR. So this remaining constant for uniform wear. So this remaining constant for uniform wear. So this both quantity comes out. Now when this quantity comes out, we are taking the maximum pressure when the innermost diameter. Because of this principle which I have explained just before. So P is inversely proportional to R when R is the least. So where pressure is maximum, from this basis we have considered this PA d by 2. This is the constant. This is the constant. This is the constant, because I could constant the maximum, the minimum pressure, the maximum diameter, but I have considered the maximum pressure and the minimum diameter. So based on this, we have done this. So we have integrated this constant. Now on integration we get this value. On integration we get this value. So when we integrate, we get this value. So after this, we see that we put the value of this d by 2 and get the expression of the pressure in this format. Get the expression of pressure. See, you get the expression of pressure in this format. Not sorry, again, it's not pressure. It should be applied load. It was the applied load. This is applied load. This applied load. This applied load. Total applied load. That is the applied load, not for the uniform area, but the total inner cone of the clutch. So this applied load, we have get this value of this P for uniform wear theory. First we have get this for uniform pressure theory. Now we are getting this for uniform wear theory. So now again what happened, we know that over here, if you see this equation, mt into pi d, so this is the equation we have considered for uniform pressure. Now we are considering the same thing for uniform, that is a torque transmitting, we are considering for uniform wear. So for uniform wear we get this value PR square dr. Now what happened, we are taking the constant P, we are again taking the constant PA into d by 2. So this is the constant term, PA into d by 2, that is the innermost radius and the maximum pressure. This is the constant, and remaining R, the smaller, and another R is left for integration. So when we integrate this value, we get this format. When we integrate this value, we get this format. This is the ultimate equation after putting the values. Mt is equals to pi mu pa dA into d square minus d square by 8 sin alpha. So this is the form of torque transmitted to the driving shaft. That is the frictional torque transmitted by the inner cone to the driving shaft with the help of the splines. This is for uniform wear theory, and this is for uniform pressure. This torque transmitted is uniform for uniform pressure, and this torque is transmitted for uniform wear. Similarly, the applied load transmitted for uniform wear is this one, and the applied load transmitted for uniform pressure theory is this one. So this is all about the mathematical model. Now an important consideration you could see over here. That from this expression, now what happens? Basically, this formulation we have just providing this formulation in a different manner. So we have calculated this mt. We have put this mt by p. We have put this mt by p. Now when we divide it by this mt by p, we get this form. Mt by p is equals to 4 sin alpha d by t. So when we divide this mt, the torque transmitted by the uniform wear, with the torque, with the load applied to the uniform wear, when you divide, we get this form. We get this form of expression. We get this form of expression for uniform wear theory. For this, we get this form of expression for uniform wear theory. Now we could see that from this is the expression mt is equals to mu pi 4 sin alpha by d plus d. Now from this expression, an important observation you could see that as basically there are the constant terms, the constant, if we consider P, if you consider that the applied force remains constant, if you consider the inner diameter and the outer diameter, if you consider the applied force remains constant, if you consider the outer diameter of the inner cone and the inner diameter of the inner cone remains constant and coefficient of friction remains constant, then we could write that mt is inversely proportional to sine alpha. Mt is inversely proportional to sine alpha. That basically indicates that as alpha, so as alpha is, if alpha is decreased, the torque transmitting capacity of the cone clutch will increase. So as alpha is decreased, the torque transmitting capacity of the cone clutch will increase. So if we deduce the value of alpha, what happens? The torque transmitting capacity of the cone clutch will increase. but there is a limit. If you continually go on decreasing, if you continually go on decreasing the value of the alpha, it looks like very interesting. We get more and more torque transmitting capacity, more torque. So with the help of the less amount of force, less force, we could get a more amount of torque turning capacity. Less applied force is required, and we are getting more amount of torque. But there is a limitation, because if alpha becomes less than the coefficient of friction or for static friction, then what happens? Then self engagement will take place. So here I am shown that if alpha if this value of alpha becomes less than phi, what is phi? An angle of coefficient of static friction, then what happens? Self engagement will take place. Self engagement will take place. So we should go for reduction of alpha, but we should not reduce alpha beyond phi, that is angle of coefficient of static friction. So for that reason, we have chosen for a given value of mu is equal to 0.2, coefficient of friction mu is equal to 0.2, taking coefficient of friction mu is equal to 0.2, we have taken alpha is equals to 12.5 degree. We get alpha 12.5 degree. Now we could see that but another limitation is also there. If we go on increasing the alpha more, if we get the value of if we go on decreasing, there is a weighting action. I've told that. So we have, that is the alpha is okay. Now one thing is that this is the, so basically we have taken alpha is equals to 12.4 for a coefficient of friction 0.2. Now so we cannot go beyond phi. So normally it is accepted that the value of alpha is taken normally as 12.5 degree. Now if you see that, if we compare with a single plate clutch and with the multi-plate clutch, with the single plate clutch and with a cone clutch, what are the advantage? Why we have done? What is the amount of wedge action we used to get? So you could see that for single plate clutch, the torque transmitting capacity is given by this one. Mt is equals to my pi p by 4 into d plus d. Now what happens when we consider the torque transmitting capacity of a cone clutch, we get this expression, that is mu pi 4 sin alpha d by d. So now when we divide this equation, that is we divide this the cone clutch, if we divide this the expression of the cone clutch with the expression of the single plate clutch, normal clutch, plain clutch, so we get this form. So it comes 1 by sin alpha. So that is torque transmitting capacity of the cone clutch by torque transmitting capacity of the plate clutch becomes equals to 1 by sin alpha. So if the value of alpha is taken 12.5, it becomes 4.22. So from this expression, it is clear that the torque transmitting capacity of the cone clutch is higher than that of the plain clutch. So that is why, that is the reason behind it. I have discussed the cone clutch is taken. But by using the which way the boundary conditions to be taken for solving the integration from the elemental area to the whole clutch depends on two theories. The number one is the uniform pressure, and for which we have calculated the applied force, applied load required, and we have also calculated the frictional torque which is required to transmit, and we have also calculated for uniform wear theory. From uniform wear theory also we have calculated the load applied, what is the value of the load applied required, and what is the torque transmitted. So that's end about of the cone clutch. Next class we should be dealing with some problems. Thank you. If you like my video, put a thumb mark to it. Have a good day.